In our next unit, Chapter 9, we will be studying the equations and graphs of conic sections. Conic sections are curves that result from the intersection of a right circular cone and a plane, which is just a flat two-dimensional surface. We can see in the diagram here that if that flat two-dimensional surface, think of it being a piece of paper, were to cut through the cone at different angles, we have four resulting shapes. Today we're going to focus on the equation and graph of the ellipse. In tomorrow's lesson, we will look at the hyperbola, and the day after that will be the parabola. Here are four sample equations that will result in the oval-shaped curve called an ellipse. As I graph each equation, study the equation and the graph, and what do you notice? Hopefully you saw that the endpoints of the ellipse on either end, those are called the vertices, they are just the square roots of the denominator matching the variable that it's underneath. So underneath the x squared we have the 9, so in the x direction the square roots of 9 are positive 3 and negative 3. Under the y squared, we have 4. The square roots of 4 are positive 2 and negative 2, so those are the vertex points on the y-axis in the y direction. And the same pattern is true for all four of these graphs. Next, we're going to look at a more formal definition for the equation of an ellipse. An ellipse is a set of all points in a plane, the sum of whose distances from two fixed points is constant. These two fixed points are called foci, which is the plural of focus. I want to show you a demonstration that's going to help make sense of this definition. Here we have a piece of string, and it's wrapped around. There's two toothpicks sticking out of the paper here. Watch as I start this recording of what happens as they draw the shape. I'm going to pause it right there. So these 2 points, kind of these anchor points, these are called the focus points or the foci. And the distance, if you were to measure the distance of the string from here to the point, also to the other focus point, and if you were to add those together, getting the sum, that distance is going to be constant as the point moves around the circle. So if it moves there, we see that this plus this is going to equal the same thing. And even if it moves over here, these two distances, again, are going to add to the same thing. And so that is the formal definition of an ellipse. The set of all points, the sum of whose distances to the foci is constant, is going to be the same. An ellipse can be elongated horizontally or vertically, as shown below. We have the center, each vertex point on the end. The major axis is the longer side, and the minor axis is what we call the shorter side. The standard forms of the equations of an ellipse centered at the origin. We have seen some examples of this so far. It appears to be in the form of a fraction, x squared, y squared. We've got different denominators. Notice how there's a plus sign, and also that they are equal to 1. A squared is always greater than b squared, but see how they can be flipped? It doesn't matter where the bigger number is. It could be under the x squared or under the y squared. If we look here at the diagram, we see here is our center. A is the distance in the x direction. If the a squared is under the x squared, it's the distance from here to here. That's the square root, the positive and negative square roots. And then b is the distance in the y direction from the center going up and down. C is the focus point, and those would be those toothpick locations in that video clip that I showed you. And what we need to know, if we look down here, the distance between the center and one of the focus points is C. So that's the distance from here to here. The focus point is always going to be on the major axis. In this orientation, the major axis is vertical, and so the C distance is also vertical. And then one thing we need to know about C, I just noticed a mistake here, is that a formula that relates all of these measures is that C squared is A squared minus B squared, and this is why we need to say that A squared is greater than B squared, because we want to do the larger number subtracting the smaller number. To get C squared, once we know C squared, we're going to do the square root, and that will give us the distance from the center to the focus point, which again is that toothpick location. All right, let's look at another example where we're going to make the graph and also locate the foci. So we can start by looking at the denominator of the x squared is 25. The square roots of 25 are -5 and 5. And the denominator of the y squared is 16. The square roots are +4 and -4. Let's go ahead and connect these to make it into that oval-shaped ellipse. My oval is not perfect. I'm sure yours looks better. Imagine it's a more rounded oval. All right, and let's also recognize that the center of this ellipse is at 0, 0. We'll see some examples of some equations later on where the center is not at 0, 0. Okay, so we've done the first step of graphing the ellipse. Second, we need to locate the foci, and so we're going to use that equation. C squared is A squared minus B squared. A squared is the larger denominator, so A squared is 25 and B squared is 16. So when we put that over here into our formula, 25 minus 16, we get C squared is 7. And when we, no, not 7, 9, another C squared is going to be 7. I think it's in the next problem. Okay, so C squared is 9. So when we take the square root, we get 3. And again, this represents the distance from the center to a focus point. Okay, now we know that the focus points, the foci, are going to lie along the major axis. So let's actually draw a dotted line through the major axis. This is going to be on the x-axis because this side is longer. And let's also put in the center. So the distance from the center to each focus point is 3 spaces. So we're going to count 3 spaces over, 1, 2, 3. And on the other side, 1, 2, 3. So these are the foci here. I'm going to highlight them. So it's good to get an idea of where they are on the graph, because when we officially say our answer, we want to do it as ordered pairs, the ordered pair location of each point. We can see here on the graph that those are both x-intercepts. So we've got -3, 0, and 3, 0. So this over here is going to be our official answer for the foci. All right, let's try this one. So doing the same thing, but we've got a different equation. This time the square roots of 49, +7, -7. Square roots of 100, 10, and -10. So this is going to be a larger ellipse. It's going to take up more of our graph space. We'll see if I can draw this one any better. The top part looks okay. Kind of looks like an egg shape there. Okay, so again, let's acknowledge that the center of this is at 0, 0. And so we've graphed the ellipse. Now we're going to locate the foci. So we're going to do our C squared formula again. A squared is always larger. So in this case, A squared is 100, B squared is 49. And this one doesn't work out as nicely. 51 is not a perfect square number. So when we take the square root of it, that is approximately 7.14. It's helpful to know the decimal approximation when we're sketching the point on our graph. And so the major axis this time is along the y-axis. It's vertical. So the distance from the center to each focus point is about 7 spaces. So if we go 7 spaces, a little over 7 spaces up, right about there, a little over 7 spaces down, Those would be our 2 focus points. Let me highlight those. And it's helpful to sketch them on the graph so that we can be sure that we're listing the coordinates of their location correctly. So we can see here that these are y-intercepts, so the x value is 0. Now, when we're listing them here, we are not going to do the decimal approximation. We're going to do the exact value, which is using the square root symbol. So positive square root 51 and negative square root 51. All right, so all of the equations we've seen so far have been in standard form. We might encounter something like this where it needs to be rewritten in standard form. So the general format that we've been seeing so far looks like this. It's important to recognize that it is equal to 1, and the a squared and b squared might be switched depending on where the larger number is, but this is one possibility. So we need to take our equation and we need to rewrite this so that it's equal to 1. And so we can do that through division. If we divide everything by 36, 36 divided by 36 is 1, so that helps us with the right-hand side. Now looking at the fractions here, we can simplify 9/36 is the same as 1/4, so this is 1x squared over 4, and then 4/36 is the same as 1/9, so we're going to write that as y squared over 9. This question is not asking us to make the graph, but in your homework it will ask you to make the graph of something like this. So this is that initial step that you want to add at the beginning, turning it into that standard form. All right, next we're going to look at some translations of ellipses. These are used to graph ellipses that are not centered at the origin. Notice how the new center is HK. And in the equation, it's x minus h and y minus k. That negative sign in the equation is going to cause the sign to switch when you're looking at the equation compared to what you get for your center. So let's do an example. Let's say it was x minus 5 squared over 4. Let's say we had y plus 1 squared over 9. The x value for the center would be positive 5. We're going to switch the sign. And the y value for the center would be negative 1. We're going to switch the sign. So that's something important to know if it's not centered at 0, 0. All right, so let's try one where we're going to graph an ellipse that is not centered at the origin. First, we're going to look at our equation and identify our centers. So remember, we're going to switch the sign, opposite sign of what we see in the equation. So the x value of our center is positive 3. The y value of our center is negative 1. Let's go over here to our graph and plot the point 3, negative 1. Now we're going to draw the rest of the ellipse the same way that we did before. So the denominator under the x squared is 9. So in the x direction, the square roots of 9 are positive 3, negative 3. So we're going to count to the right 3 spaces. And then from the center, we're going to go to the left 3 spaces. Now in the y direction, the denominator under the y squared part is 16. Those square roots are positive 4 and negative 4. So we're going to count up 4, 1, 2, 3, 4, and down 4. Go ahead and draw our ellipse shape through the 4 vertices. And the major axis, this time the major axis is parallel to the y-axis. That's where the longer side is. We've graphed our ellipse. Now we need to get the location of our foci. So we're going to do that c-squared formula again. The larger denominator, subtract the smaller one. Here's that answer of 7 that I was thinking of earlier. So we've got plus or minus the square root of 7. Now when we go to sketch this on our graph, we can put this into our calculator to see that the square root 7 is approximately 2.6. So when we go over here to, we're going to start at our center. It's going to be on the major axis. So we're going to move up or down. We're going to go up 2.6 spaces, so that's right about here. And then from the center, we're going to go down 2.6, so that's right about there. Let me highlight those foci points. And now we're going to give their location as an ordered pair. The x value for each one of these points is 3. Notice how we've not changed in the x direction. We have not moved left or right from the center. It's still at 3. Now, in the y direction, we are moving, and so we started at a y value of -1. We added square root 7 to get this point, and then starting at -1, we subtract square root 7 to get that point. And that's exactly how we're going to write them out. No decimal approximations here. We're going to do the exact value using the square root symbol. So these foci are a little harder to get when it's not centered at 0, 0. But notice how, oh, I just realized a mistake there. That should be -1. Notice how the center is part of the foci. We just want to make sure that we're adding and subtracting the c value to the correct coordinates. So in this case, it's the y values because we can visually see we drew them up and down because the major axis was in the y direction. In this next problem, we are going to work backwards using some given conditions. They've given us the coordinates of the foci and the vertices. We want to find the standard form of the equation. So we're going to start by just graphing these points. So the foci are at -3, 5, 1, 5. And then the vertices are -7, 5, and 5, 5. So the ellipse is going to pass through our vertices. It's going to be something like this. We're not going to draw it because we just don't know how tall it's going to go, how high up or how low it's going to go. But looking at the foci to start, we can actually count inwards in between. So there's 4 spaces in between the focus points. If we go 2 spaces in on either side, we're going to get to the center. So that's the first thing that we can determine, that this center is at -1, 5. Let me rewrite that there. It's supposed to be a 5. All right. Let's continue by putting the standard form of our equation so that we kind of know what we're looking for. So since it's not centered at 0, 0, it's going to be x minus h squared over a squared, y minus k squared over b squared equals 1. So we already know h and k because that's based on our center. Now, the distance from the center point, the distance from the center to the vertex in this direction here is 6 spaces. And so we're going to say that A is 6. So that's going to go under the x. So let's actually just start to fill these in. So that's actually going to be a 36. For our center, this is going to appear to be x plus 1, changing the sign. Over here for the y value, that's going to appear to be y minus 5. So it looks like really what we just need to find out is b squared. So b is the distance from the center to the vertex going in the vertical direction. So luckily we have the c squared formula that can help us to solve for b squared. We already know what a is. A is 6, so a squared would be 36. And now we're going to use the information of the foci to find the value of c. So the foci, the c distance, is the distance from the center to each focus point, which is 2 spaces. It is this distance right here. So we see that c is 2, so 2 squared is 4. So solving this equation, we get b squared is equal to 32. And that's the last thing we need over here to get our equation. And one final thing, let's change that 6 squared to a 36. There we go. In the last problem, we're going to look at converting an equation from the general form into the standard form. The standard form is what we've looked at so far. It's got that x squared over a squared plus y squared over b squared equals 1. It's very easy to graph when it's in the standard form. The general form, as you can see up here, looks quite different. So we still have the x squared and the y squared. We have an x and a y. A, b, d, e, f all represent numbers, just regular numbers. It's equal to 0. We're going to use the skill of completing the square to help us turn this from general form into standard form. So just for a moment, I want to do a quick review of what it means to complete this square. So let's say we're given an expression x squared plus 6x. We can use this first diagram to represent the area of that. So x times x, so this part here will be x squared. Let's say that this length of the piece added on to the end is a length of 6, and so the area of this piece would be 6x. So notice how this is a visual representation of x squared plus 6x. Now let's say we were to take this 6x piece and cut this in half and move half of it to the top and the other half down here to the bottom. So let's label the sides in this new picture. The big square will still be x times x. Since we cut this in half, now this little length will only be 3. So we've got 3 up here and 3 down there. And so what's highlighted represents the original area that we had, the x squared plus 6x. We are going to add in a piece right here to complete the square. So see, we want to make this a perfect completed square, and the area of this piece, if we look at the side lengths, 3 times 3 is 9. And so going back to the original expression, if we add 9 onto the end of it, we have literally completed the square. This is helpful because now we've turned this into a perfect square trinomial, and we can factor it into something that looks like this. So if we think about two numbers that multiply to 9 and add to 6, we get 3 and 3. So we've got x plus 3 times x plus 3, so we can write that x plus 3 squared.